Hey everyone, today we'll be going over section 1.8, Inequalities, and section 1.9 about the coordinate plane and graphs. So starting off with inequalities, solving an inequality is the process of finding the set of numbers that make the inequality a true statement. So usually inequalities have infinitely many solutions, which form an interval or unions of intervals on the real line. And we usually use set builder and interval notation to represent the solutions to inequalities. So we'll go over interval notation here and the different kinds, and then also what it looks like in set builder notation. So let a and b be in the real numbers such that a is less than b. So our interval notations are the ones on the left, as we can see. So we have open intervals, closed intervals, and infinite intervals. So an open interval is represented with parentheses, and so these include the real numbers between, but not including a and b. So it's just the numbers between a and b, and we represent this as that in set interval notation. So we have a and b parentheses, so x such that a is greater than a but less than b. And in a graph, we do this by having open dots, which means that they're not including a and b. And then the solutions are all those numbers in between, so I have it shaded green. A closed interval is represented with brackets at the end, and these are the real numbers between a and b and including a and b. So our set builder notation, we have x is greater than a or equal to, and x is less than or equal to b. And so in a graph, we have these as closed dots. So see how compared to open interval, the open interval has open, and then the closed interval has closed dots. An infinite interval is a to infinity. And so these just represent the real numbers that are greater than a. And so when we draw that, we have our open dot at a, and then we have an arrow just going all the way to the right, and that's to infinity. And this is just x values greater than a, not including a. That's why we have the open dot. And then for intervals with closed dots, we have an infinite interval from negative infinity to b. And these are real numbers that are less than or equal to b. So we have the closed dot, and then we're going to the left for negative. We could have an infinite interval where real numbers are greater than or equal to a, and then to infinity. But these are just the different ways to do it. And the same thing for the closed. With b, it could be open, but here we have it closed. And for the infinity and negative infinity, we always have parentheses with those. We don't have closed brackets. Alright, so here's an example. I have negative 1 to the 4. So I have x is less than negative 1. X is greater than negative 1. And x is less than or equal to 4. So here I have the closed dot on... Oh, sorry, that's a parenthesis. I'll make it a little bit clearer. Okay. So we have the open dot on negative 1, and then the closed dot on 4, because it's x is greater than negative 1, but it's not equal to it. And then x is less than 4 and equal to it. So the intersections of and unions of intervals. So we have 1, 4... intersecting with 2, 8. So that's A. So we'll do that one first. So the first thing I did was just draw the intervals for both. So I have 1, and then I draw it all the way to 4, and then it's also open. And then I draw the 2 to 8. So I have the closed, and then I do all the way to 8. And it includes that too. So the intersection is what values are in common to both. So what values are in the left interval and the right interval. So we know that 2 is included in both. because that's where the green and the red overlap. So we're looking for those values. So it's 2 to 4 is the overlap, but then we also don't include 4 because it wasn't in the green. So our interval is 2 with the closed bracket and then 4 with the open. B is the union of these. So we still have the same graph here, but we want to know what was in the left interval or the right interval. So we start at 1, and then it goes all the way to 8, but our 8 is closed and our 1 is open. So it's just what's in the red or what's in the green. So our interval is 1, 8. And then here's some rules for inequalities. So A is less than or equal to B. If we add C to both sides, since it's the same number, we're keeping that inequality the same. And then if we subtract, so this first rule is just adding. The second rule, if we're subtracting the same number, the interval is the same. And then 3 is if C is greater than 0 and A is less than or equal to B, when you multiply by a positive C, the inequality also stays the same. However, if C is less than 0 and A is less than or equal to B, when you multiply by a negative number, the inequality flips. So make sure you catch that. So here we have less than or equal to, but then it flips. And then so C times A is greater than or equal to C times B when you multiply by a negative number. If A is greater than 0 and B is greater than 0 and A is less than or equal to B, for our fifth rule, it's saying that the fraction of 1 over A is greater than or equal to the fraction of 1 over B. Our sixth rule states if A is less than or equal to B and C is less than or equal to D, then when we have A plus C, that's going to be less than or equal to B plus D, because A and C are both less than or equal to B and D. And then this last rule is like the transitivity rule. So if A is less than or equal to B and B is less than or equal to C, then our A is also less than or equal to C, because B is also less than or equal to C. So the most important rule is to remember, if we're multiplying or dividing each side by a negative number, then we reverse the direction of the inequality. So here's an example. So say I have 3 is less than 5. If I multiply by 2, the inequality still holds. However, if I multiply by negative 2, the inequality flips. So the key to solving linear inequalities, it's similar to solving a linear equation, but we isolate the variable on one side like that. But we read them a little bit differently. But here's some examples of linear inequalities. So here's some common English phrasing to describe inequalities that I've been using throughout this video so far. So we have x is at least 5, and then that means x is greater than or equal to 5. So it's at least 5. So we can't go anywhere lower than 5 is what it's saying, because x is greater than or equal to 5. And then so you guys could look through those. X is between 5 and 7. That's going to be here. X is at least 5 is here. X is at most 5. X is no more than 5. And x is no less than 5. Alright, here we have an example of solving one of these linear inequalities. So I have 3 minus 2x is less than or equal to 11. So I'm going to solve it like I would a linear equation. I'm going to subtract 3 from both sides. I get negative 2x is less than or equal to 8. I divide by 2, and now I have x is greater than or equal to negative 4. So remember, I divided by negative 2. That's why I flipped the inequality symbol. So if we graph this solution, we have x is greater than or equal to negative 4. So since it's greater than or equal to, that's a solid dot. And then I want my solutions to be greater than negative 4 also. So I put the green all the way going right. Here's another example. I have negative 2x minus 4 is greater than x plus 5. So I want to group the like terms. So I'm going to subtract x over, and then I get negative 3x minus 4 is greater than 5. I'm going to add the 4 to the right. I get negative 3x is greater than 9. I'm dividing by negative 3. So that means we flip our symbol. So x is less than negative 3. So since x isn't equal to negative 3, I have my open dot. And I want the values of x that are less than negative 3. Therefore, my arrow is going to shade to the left. Okay. Now here's an example of where we're solving a pair of simultaneous compound inequalities. So here I have two separate inequalities. I have negative 3 is less than 2x plus 1, and 2x plus 1 is less than or equal to 3. So I could just combine those two. So negative 3 is less than 2x plus 1. Therefore, negative 3 is also less than 3. And our 2x plus 1 is less than or equal to 3. So I just combine those two. And our goal here with the compound inequality is to isolate x in the middle. So whatever we do to the middle expression, we also do to the inequality on the left, negative 3, and the inequality on the right, 3. So now we'll solve and graph. So I'm subtracting 1 from the middle. So I'm going to do that to the left and the right. So I get negative 4 is less than 2x and is less than or equal to 2. I'm going to divide 2 from the middle, so I'm going to do that to the left and right also. And then I get negative 2 is less than x, which is less than or equal to 1. So in order to graph that, so my x values are going to be between negative 2 and 1 essentially. So I'm not including negative 2 because it's not equal to, so I put my open dot, and I'm including 1 because it's equal to it. So I put my closed dot, and then my shading is the values that are in between those. So solving nonlinear inequalities is a little bit trickier, but here's some guidelines to help us through, and then we'll go through an example. So in solving nonlinear inequalities, our guidelines are to move all terms to one side. Then we will factor. Then we will find intervals using factors and zeros to split up intervals. We will make a diagram to test the values. We will solve using a sign table to find intervals where the inequality is satisfied and then check endpoints. So for example, we have x squared is less than or equal to 5x minus 6. Okay, so our first step is to move all terms to one side. So we're going to move minus 5x plus 6 to get everything to the left. So we have x squared minus 5x plus 6 is less than or equal to 0. We can see this is a nonlinear inequality because it's x squared, which makes it quadratic. Now we're going to factor. So our factors are x minus 3 and x minus 2. So this is 0 when x equals 3 and x equals 2. So we're going to now split it up into intervals and use our zeros. So our different intervals are negative infinity to 2, because that's when it's 0. And then we have 2 to 3, and then 3 to infinity. So we're using our zeros. So we're doing negative infinity to 2 because 2 is our 0. we're doing the space in between, and then we're also doing the space after 3. So here on the right, you can see our diagram. So we have negative infinity to 2 is an interval, 2 to 3 is an interval, and then 3 to infinity, because our zeros are the red dots. So we're going to choose a number inside each interval and check the sign. So we have negative infinity to 2. We're using our test value of 1. So we plug that into our factors. So we have 1 minus 2 equals negative 1 less than 0. X minus 3 is negative 2 less than 0. And then for our different intervals, 2, 3, and 3 infinity, I use test values at 2.5 and test value 4. So now I'm going to make a table. So I have the sign of x minus 2, the sign of x minus 3, and then my sign when I multiply these two. So, and then I have my intervals lined up. So we know our sign of x minus 2 was negative because it was negative 1. The sign of x minus 3 was negative 2 for the interval of negative infinity to 2. And so for 2 to 3, it's plus, minus. So then we multiply them to get the sign of x minus 2 times the sign of x. Oops, I forgot my x in there. Of x minus 3. Okay, so negative times a negative is positive. Positive times negative is a negative. And then positive times positive is a positive. So here we can see that our inequality is satisfied when it's negative. And that's because our factors, x minus 3 times x minus 2 is less than or equal to 0. Therefore, we were looking for a negative. The positive values don't satisfy that. So now we know our interval is 2 to 3, and then we check our endpoints to see if 2 and 3 are included in it. So we do an endpoint check. So we do 3 minus 3 times 3 times 2. 3 minus 2, is less than or equal to 0. And then we plug in 2 into our factors. And then we have 2 minus 3 times 2 minus 2 is less than or equal to 0. Therefore, they satisfy the inequality, so it's closed. So our answer is x such that 2 is less than or equal to x, and x is less than or equal to 3. And we have our closed brackets. If the endpoints didn't satisfy the inequality of our factors, then it would be open parentheses. Also, if our factors changed sign, so if it was from, if our interval between the 2 and the 3 zeros, since our zeros are both positive, we're fine. But say it was like a negative factor and a positive factor, then we would have to test 2 different values with 2 different signs. Okay, here's another example. So we have 1 plus x over 1 minus x is greater than or equal to 1. So first, we're going to move all of our terms together. So I'm going to subtract 1, and then I'm going to subtract 1 from here too, and then, oops. So that zeroes out. And then I'm going to combine the fractions. So I'm going to combine 1 plus x over 1 minus x minus 1. And that is by doing the greatest common denominator. And then, least common denominator. I'm going to have 1 plus x minus 1 plus x over 1 minus x is greater than or equal to 0. So I'm just combining the fraction here. So I have 2x over 1 minus x is greater than or equal to 0. So our factors are 2x and 1 over x. So our fraction is 0 when x equals 0 and x equals 1. So we're going to split up our intervals. So here we have 0, 1, 2, -1. So I'm going to mark the zeros here. So I have 0 and 1 to make my intervals. So I have negative infinity to 0 here, 0 to 1 here, and 1 to infinity there. So I have my factors 2x, 1 over 1 minus x, and then 2x over 1 minus x. And then I'm going to do my test values in between those intervals. So you could choose whichever. But I ended up with negative, positive is a negative. For negative infinity to 0. For 0 to 1, I got positive, positive, positive. And then 1 infinity, I got positive, negative, and negative. So go ahead and try that on your own with your own test values. And so the only one that satisfies the inequality is the positive one. And that's because our 2x over 1 minus x is greater than or equal to 0. So now we're going to check our endpoints. So our endpoints are 0 and 1. So I check 0 and I get 2 times 0 over 1 minus 0, which is 0, which is greater than or equal to 0. So that one's good. I check 1 and I get 2 times 1 over 1 minus 2, which is negative. Therefore, it's not greater than or equal to 0. So our answer is 0 to 1. However, there's a parenthesis around the 1. So I have an open dot at 1. Now, I also have absolute value inequalities. So these tell us that the absolute value of something is the distance from x is either greater than a number, or it's less than a number, or it's equal to something. So I have here an example of the absolute value of x is less than 2. So that tells me that the distance of x from 0 is less than 2. Therefore, I have here's 0. And so my x's can be any of these values here, as long as they're not greater than 2 from 0. So my distance here is 2, my distance here is 2. So I just want something that's less than 2. If my absolute value of x is greater than 2, that means the distance of x from 0 is greater than 2. So my x is less than -2, or my x is greater than 2. And then I give the interval notation here. But basically, I want my distance from 0 to be greater than 2. So if my values are this way, they're greater than 2. And then if my values are this way, they're also greater than 2. So just be careful about, for negatives, even though I'm going to the left, that means that my distance from 0 is still pretty great. It's not a negative value because distance is always positive. So here's some properties of absolute values, inequalities, and how to solve. So here, my absolute value of x is less than c. This is how I would write it as a compound inequality because of the absolute value. So I know that my x is greater than -c and my x is less than c. If x is less than or equal to c, that means that my x is greater than or equal to -c and my x is less than or equal to c. And then here's the pictures of the graphs over here. So that just means that they're in between my -c and c, the x values that I want. And then it's closed versus open dots for those. If my absolute value of x is greater than c, that means that x is less than -c or c is less than x. And that's the one where our values could be to the right or to the left of our c values because we want it to be greater than. So if my absolute value is greater than or equal to c, that means x is less than or equal to -c, or c is less than or equal to x. Okay. And that's because here we could see our c and our -c. So if our x is less than or equal to negative c, that's going to be the values over here, our negative values. If c is less than or equal to x, that means our x is greater than or equal to c. So it's going to be that way. So here's an example so we could test that out. So I've solved and graphed the absolute value x minus 4 is less than 3. This means, using our rules, that we have negative 3 is less than x minus 4, and then 3 is greater than x minus 4. So my goal is to isolate x in the middle, so I'm going to add 4, and I get 1 is less than x, and then 7 is greater than x. So when I graph that, my x values can be between these, and then it's open dots because they're not including 1 and 7. So here's another example. I have negative 2 times the absolute value of 3x plus 5 plus 7 is greater than or equal to negative 13. So something different about this one is that we need to isolate that whole absolute value symbol before we start applying our rules to break up our inequality. So I'm going to subtract 7 and divide by negative 2 to both sides. And then I have the absolute value of 3x plus 5 is less than or equal to 10. Now I can break up my inequality. So I'm going to use my rules. So I have negative 10 is less than or equal to 3x plus 5, and 10 is greater than or equal to 3x plus 5. I'm going to subtract 5 from both sides to isolate my x, divided by 3. And then I get negative 5 is less than or equal to x, and then 5/3 is greater than or equal to x. So I have my graph here. I have my negative 5, and then this is 5/3. So my x values are the values between these two, and then it's closed dot because it includes those values. Alright, another example here. So I have 7 is less than the absolute value of 5 minus 2x. So I'm just going to flip this around, just the expressions, but when I flip them, I'm going to make sure my inequality, well, I'm going to take that out so it doesn't look like or equal to. So I'm just going to flip them just so I can have this expression over here. But make sure you keep the same one of these. So 5 minus 2x is still greater than 7. So using my rules, I'm going to use 5 minus 2x is less than negative 7, or 5 minus 2x is greater than 7. So I'm going to solve these separately and then take the union. So I'm just going to do the left-hand side first, subtract 5, and then I get negative 2x is less than negative 12, divided by negative 2, flip the sign, division by negative, and then I get x is greater than 6. The same thing to the right side, but we end up with x is less than negative 1. So I'm going to take the union of these. So I have x is greater than 6. Therefore, my values are between 6 and infinity. And x is less than negative 1. So my values are between negative 1 and negative infinity. So on a graph, we have the solutions going in two opposite directions. And then our dots are open because they don't include 6 and negative 1. Okay. Here we're going to do an applied example of an inequality. So Lowry Car Rental Agency charges $4 a day plus 15 cents per mile, whereas Delk Rental charges $20 a day plus 5 cents per mile. How many miles must be driven to make the daily cost of Lowry rentals better than the deal of a Delk rental? So here we're going to let x be one unknown quantity. So x is our number of miles driven in a day, because we want to know how many miles must be driven in order for the cost of one company to be better than the other. So x equals number of miles driven in a day. Okay, now we're going to write an inequality that models these conditions. So we know that Lowry is a better deal if the daily cost is less than Delk's, because we want to know how many miles must be driven to make the daily cost better. So if the daily cost of Lowry is less than the daily cost of Delk, then we're good to go. So I'm going to write the numbers with the miles that expresses this. So we have $4 a day. That's just a flat rate. So for Lowry, it's 4 plus 15 cents times X, because it's 15 cents per mile, is less than 20 is the flat rate of Delk, plus 5 cents times X, because it's 5 cents per mile charged. And then we just solve for X. So I'm going to subtract 4 and then and then subtract my 5 cents X to the left. So I get 0.01X is less than 16. I divide by 0.01 and I get X is less than 160. What does this mean in words? Well, that means driving fewer than 160 miles a day makes Lowry a better deal. And then we check the solution just to make sure that it makes sense and it's logical and it checks through that we didn't make any sort of numerical errors. So we have 4 plus, and I'm just going to choose something less than 160. I chose 150 times 0.15 is $26.50 for Lowry. Checking with Delk, I have 20 plus 0.015 times 150. That's $27.50. Therefore, Lowry is better than Delk in that case. Okay, great. I'm going to go ahead and end this video. And in the next video, we'll go over section 1.2, the coordinate plane. See you then.